Hello and welcome to Earth Science, Lecture 20, Clouds and Precipitation. To review briefly, condensation occurs when water vapor in the air changes to a liquid. The result of this process may be either dew, fog, or clouds. For any of these forms of condensation to occur, the air must be saturated. Saturation occurs most commonly when air is cooled to its dew point, or, less often, when water vapor is added to the air. Under normal atmospheric conditions, condensation occurs only when a surface exists on which the water vapor can condense. When dew forms, objects near the ground, such as grass and car windows, serve this purpose. But when condensation occurs high above the ground, tiny bits of particulate matter, known as cloud condensation nuclei, serve as the surfaces for which water vapor can condense on. These nuclei are very important, for in their absence, a relative humidity well in excess of 100% is needed to produce clouds. Condensation nuclei, such as microscopic dust, smoke, pollen, and salt particles from the ocean, are profuse in the lower atmosphere. Because of this abundance of particles, relative humidity rarely exceeds 101%. Some particles, such as ocean salt, are particularly good nuclei because they absorb water. These particles, termed hygroscopic, which hydro means moisture, scopic means to seek, nuclei. When condensation takes place, these tiny cloud droplets grow quickly at first, but their growth slows as they use up the excess water vapor. The result is a cloud consisting of millions upon millions of tiny water droplets, all so fine that they remain suspended in air. When cloud formation occurs at below freezing temperatures, tiny ice crystals form. Thus, a cloud may consist of both water droplets and ice crystals. Clouds are among the most conspicuous and observable aspects of the atmosphere and its weather. Clouds are forms of condensation best described as visible aggregates of minute droplets of water or tiny crystals of ice. In addition to being prominent and sometimes spectacular features in the sky, clouds are of continual interest to meteorologists because they indicate what is going on in the atmosphere. In 1803, English naturalist Luke Howard published a cloud classification scheme that serves as the basis of our present-day system. According to Howard's system, clouds are classified on the basis of two criteria: form and height, as you can see in the image. We will look at the basic cloud forms, that is, shapes, first, and then we'll examine cloud heights. So keep this image in your mind as we move forward. Clouds are classified based on how they appear when viewed from the surface of the Earth. The basic forms or shapes are cirrus or cirriform clouds, which are high, white, and thin. They form a delicate veil-like patch or wispy-like strands that often have a feathery appearance. Note that cirrus is the Latin word for curl or filament. Stratus or stratiform clouds consist of sheets or layers, that is, strata, that cover much of the sky. And cumulus or cumuliform clouds consist of globular cloud masses that are often described as being cotton-like in appearance. Normally, cumulus clouds exhibit a flat base and appear as rising domes of towers. Note that cumulus means to heap or pile in Latin. Cumulus clouds form within a layer of the atmosphere where there is some convection and rising air. All clouds have at least one of these three basic forms, and some are a combination of the two. For example, stratocumulus clouds are mostly sheet-like structures composed of long parallel rolls of broken globular patches. In addition, the term nimbus, which is Latin for rain cloud, is added to the name of a cloud that has that produces any types of precipitation. Thus, nimbostratus, for example, denotes a flat-lying rain cloud. Next, let's look at cloud height. In terms of their height, clouds are classified as either high, middle, low, or clouds of vertical development. High clouds form in the highest and coldest regions of the troposphere and normally have bases above 6,000 meters or 20,000 feet. Temperatures at these altitudes are usually well below freezing, so the high clouds are generally composed of ice crystals or supercooled liquid droplets. Middle clouds occupy heights from 2 to 6,000 meters or 6,500 to 20,000 feet. And they may be composed of water droplets or ice crystals, depending on the time of year and the temperature profile of the atmosphere in that location. And then last are the low clouds. Low clouds form near Earth's surface, up to an altitude of about 2,000 meters or 6,500 feet, and are generally composed of water droplets. Clouds that extend upward to span more than one height range are called clouds of vertical development. The altitudes at which high, middle, and low clouds occur can vary somewhat with seasons and with latitude. For example, at high or poleward latitudes and during cold winter months, high clouds generally occur at lower altitudes. So let's go ahead and step through each type of cloud. So again, let's refer back to that figure. It's going to take me a second here. So notice there are many different types of clouds shown. So what we're going to do is quickly step through each of them. Okay, let's start with the high clouds. 3 cloud types make up the family of high clouds, that are those that are above 6,000 meters or 20,000 feet. We have cirrus, cirrostratus, and cirrocumulus. Cirrus or CI clouds are thin and delicate and sometimes appear as hooked filaments called mares or tails. As the name suggests, cirrocumulus or CC clouds consist of fluffy masses, whereas cirrostratus or CS clouds are flat layers. Because of the low temperatures and small quantities of water vapor present at these high altitudes, all clouds, or all high clouds, are thin and white and are made up mostly of ice crystals. Furthermore, high clouds do not produce precipitation that reaches the surface. However, when cirrus clouds are followed by cirrocumulus clouds and increased sky coverage, they may warn of impending stormy weather. Next are the middle clouds. Clouds that appear in the middle range, that is 2 to 6,000 meters or 6,500 to 20,000 feet, have the prefix alto as part of their name. Altocumulus or AC clouds are composed of globular masses that differ from cirrocumulus clouds in being thicker and denser. Altostratus clouds or AS clouds create a uniform white to grayish sheet that covers the sky, with the sun or moon visible as a bright spot. Infrequent light snow or drizzle may accompany these clouds. And last are the low clouds. There are 3 members in the family of low clouds, those below 2,000 feet or those below 2,000 meters or 6,500 feet. Stratus, stratocumulus, and nimbostratus. Stratus, or ST clouds, are a uniform fog-like layer of clouds that frequently covers much of the sky. These clouds sometimes produce light precipitation. When stratus clouds develop a scalloped bottom that appears as long parallel rolls or broken globular patches, they are called stratocumulus, or SC clouds. Nimbostratus, or NS clouds, derive their name from the Latin term nimbus, which means rain cloud, and stratus, which means to cover with layers. Nimbostratus clouds tend to produce constant precipitation and low visibility. These clouds normally form under stable conditions when air is forced to rise as along a front. Such forced ascent of stable air leads to the formation of a stratified cloud deck that is widespread and that may grow into the middle level of the troposphere. Precipitation associated with nimbostratus clouds is generally light to moderate, but can be heavy, and is usually of long duration, covering a large area. Some clouds have their bases in the low height range, but extend vertically upward into the middle or high altitudes. Consequently, clouds in this category are called clouds of vertical development. These tend to be associated with unstable air, which rises because of their own buoyancy. Although cumulus clouds are usually connected with fair weather, they may grow dramatically under the proper circumstances. In fact, when I'm storm chasing, I do look for clouds like this because these are the guys that can build up into giant towers like you see below if the conditions are favorable. Once upward movement is triggered, acceleration can be powerful, and clouds with great vertical extent may form. The end result is often a towering cloud called a cumulonimbus or CB cloud, which usually produces moderate to heavy rain showers or thunderstorms. Definite weather patterns can often be associated with particular clouds or certain combinations of clouds, so it is important to become familiar with cloud descriptions and characteristics. So now let's shift gears slightly and talk about clouds near the surface. Fog. Fog is defined as a cloud with its base at or very near the surface. Physically, there is no difference between fog and a cloud. Their appearances and structures are all the same. The essential difference is the method and place of formation. While clouds mainly form when air rises and cools adiabatically, fog occurs because air is either cooled below its dew point temperature or gains water through the evaporation process until it becomes saturated. Fog is considered an atmospheric hazard because it reduces visibility. Official weather stations report fog only when it is thick enough to reduce visibility to 0.6 miles or less. Dense fog can cut visibility to a few dozen meters or less, making travel by any mode difficult and dangerous. So here's a great image of fog. We've probably, I hope, all experienced fog. And here is an actual aerial picture of it. So you can actually see fog sitting between these two mountain ranges. So it turns out that there are multiple types of fog, just like there are multiple types of clouds. So let's look at each. When the temperature of a layer of air in contact with the ground falls below the dew point temperature, condensation produces fog. Depending on the prevailing conditions, fog formed by cooling is either called radiative fog, advection fog, or upslope fog. As the name implies, radiation fog results when ground cooled by radiation cools the overlying layer of air. It is a nighttime phenomenon that requires clear skies and a high relative humidity. As the night progresses, a thin layer of air near the ground is cooled below its dew point, resulting in the formation of fog. Because the air containing the fog is relatively cold and dense, it flows downslope in hilly terrain. As a result, radiation fog is thickest in valleys, whereas the surrounding hills may remain clear, like you see in the image. Normally, radiation fog dissipates after 1 to 3 hours of sunrise. The common phrase that fog lifts is misleading. Actually, as the sun warms the ground, the fog is just evaporating from the bottom up. The next type of fog is advection fog. When warm, moist air blows over a cool surface, it becomes chilled by contact with the colder surface below. If cooling is sufficient enough, the result is a blanket of fog known as advection fog. And note, the term advection refers to air moving horizontally. A classic example is the frequent advection fog found around San Francisco's Golden Gate Bridge. The fog experienced here, as well as many other West Coast locations, is produced when warm, moist air from the Pacific Ocean moves over the cooler California coast. Advection fog is also common in the wintertime in the southeast and Midwest when relatively warm, moist air from the Gulf of Mexico and the Atlantic moves over cold and occasionally snow-covered surfaces to produce widespread foggy conditions. This type of advection fog tends to be thick and produce hazardous driving conditions. When relatively humid air moves up a gradually sloping landform, or in some cases up the steep slopes of mountains, upslope fog can form. Because of that movement, air expands and cools adiabatically. If the dew point is reached, an extensive layer of fog will form. It is easy to visualize how upslope fog might form in mountainous terrain. However, in the United States, upslope fog can occur in the Great Plains when humid air moves from the Gulf of Mexico toward the Rocky Mountains. Recall, of course, that Denver, Colorado, for example, is the mile-high city and that the Gulf of Mexico is at sea level. So air flowing up the Great Plains expands and cools adiabatically by as much as 12 degrees Celsius, which can result in an extensive upslope fog in the western plains. We also have steam fog. When air forms fog, mainly because of the addition of water vapor, the fog is called an evaporation fog. Two types of evaporation fogs are recognized: steam fog and frontal fog. We'll look at both. When cool, unsaturated air moves over a warm body of water, enough moisture might evaporate to saturate the air directly above. This will generate a layer of fog. The added moisture and energy often makes the saturated air buoyant enough to rise. Because the foggy air looks like steam, we give it the appropriate name of steam fog. It looks similar to, say, the steam that forms above a hot cup of coffee. Steam fog is a fairly common occurrence over lakes and rivers on clear, crisp autumn mornings when the water is still relatively warm, but the air has cooled. The other type we mentioned is frontal precipitation fog. Frontal boundaries, where a warm, moist air mass is forced above the cooler, drier air mass below, we can have frontal fog develop. Fog develops because the raindrops falling from the relatively warm air above the frontal surface evaporates in the cooler air below, causing it to become saturated. Frontal fog, which can be quite thick, is most common on cool days during extended periods of light rainfall. So we now know the different types of fog and clouds, so let's discuss, of course, how they form and how we get precipitation out of them. If all clouds contain water, why do only some produce precipitation while others drift just overhead? This seemingly simple question perplexed meteorologists for many years. Typical cloud droplets are minuscule, anywhere from 0.02 millimeters in diameter, or about a quarter the width of a human hair. So because of their small size, cloud droplets in still air fall incredibly slowly. An average cloud droplet falling from a cloud base would require several hours to reach the ground, except that it would actually evaporate within a few meters in the unsaturated air below. So the question here is, how large must a cloud droplet grow in order for it to fall as precipitation? A typical raindrop has a diameter of about 2 millimeters, or about 100 times that of the average cloud droplet. However, the volume of a typical raindrop is 1 million times that of a cloud droplet. Thus, for precipitation to form, cloud droplets must grow in volume by roughly 1 million times. You have probably watched a TV documentary in which mountain climbers braved intense cold and ferocious snowstorms to scale ice-covered peaks. Although it is hard to imagine, similar conditions exist in the upper portions of towering cumulonimbus clouds, even on sweltering summer days. It is within these clouds, these cold clouds, that a mechanism called the Bergeron process generates much of the precipitation that occurs in the middle and high latitudes. The Bergeron process is based on the fact that cloud droplets remain liquid at temperatures as low as negative 40 degrees Celsius or negative 40 Fahrenheit. Liquid water at temperatures below freezing is termed supercooled, and it becomes solid or freezes upon impact with the surface. This explains why airplanes collect ice when they pass through a cloud composed of sub-zero droplets, a condition called icing. Supercooled water droplets also freeze upon contact with particles in the atmosphere known as ice nuclei, or freezing nuclei. Because ice nuclei are relatively sparse, cold clouds primarily consist of supercooled droplets mixed with a lesser amount of ice crystals. When ice crystals are supercooled, water droplets coexist in a cloud. The conditions are ideal for generating precipitation. Because ice crystals have a greater affinity for water vapor than does liquid water, they collect the available water vapor at a much faster rate. In return, the water droplets evaporate to maintain saturation and replenish the diminishing water vapor, thereby producing a continual source of moisture for the growth of ice crystals. The result is that ice crystals grow larger, at the expense of water droplets which shrink in size. Eventually, this process generates ice crystals large enough to fall as snowflakes. During their descent, these ice crystals become large as they intercept supercooled cloud droplets that freeze on them. When Earth's surface temperature is about 4 degrees Celsius or 39 Fahrenheit or higher, snowflakes usually melt before they reach the ground and continue their descent as rain. A few decades ago, meteorologists believed that the Bergeron process was responsible for the formation of most precipitation. However, it was discovered that copious rainfalls may be produced within clouds located well below the freezing level, in other words, in warm clouds. So this is particularly true in the tropics. This led to the proposal of a second mechanism through which most precipitation is produced, known as the collision-coalescence process. Research has shown that clouds composed entirely of liquid droplets must contain some droplets larger than 20 micrometers or 0.02 millimeters for precipitation to form. These large droplets usually form when hygroscopic particles, that is, particles that attract water, such as sea salt, are abundant in the atmosphere. Hygroscopic particles begin to remove water vapor from the air, and when the humidity is under 100%, and the cloud droplets that form on them can grow quite large. Because the rate at which drops fall is size dependent, these giant droplets fall more rapidly. As they plummet, they collide with smaller, slower droplets. After many such collisions, these droplets may have grown large enough to fall to the surface of the Earth without evaporating. Updrafts in storms also aid this process because the airflow propels the droplets so that they remain in the cloud longer, allowing for additional collisions. Raindrops can grow to a maximum size of about 5 millimeters, at which point they fall at a rate of 20 miles per hour. Beyond this size and speed, the water's surface tension, which holds the drop together, is overcome by the drag imposed by the air, causing the drops to break apart. The resulting breakup of a large raindrop produces numerous small drops that begin anew, and the process begins again. So this is the basic idea. So to repeat, raindrops can grow to a maximum size of about 5 millimeters, at which point they fall at a rate of 20 miles per hour. Beyond this size and speed, the water's surface tension that holds the drops together is overcome by the drag of the air imposed so far. And so again, these drops break apart. So that's what this is trying to show on the right. So we start looking at raindrops. First of all, they're not teardrop shaped like we're typically seeing in graphics. They're typically round when they begin. As they get larger, there's more drag on them. In other words, more force acting against them. So they get big enough so that they can fall, but if they get too big, too much air is pushing up in the middle and it can cause these to split into multiple drops. So now let's talk about the different types of precipitation. Atmospheric conditions vary greatly, both geographically and seasonally, resulting in several different types of precipitation. In meteorology, the term rain is restricted to drops of water that fall from a cloud and have a diameter of at least 0.5 millimeters or 0.02 inches. Most rain originates either in nimbostratus clouds or in towering cumulonimbus clouds. The latter are capable of producing unusually heavy rainfall known as cloudbursts. As mentioned in the previous section, raindrops rarely exceed about 5 millimeters in diameter because of the surface tension that holds them together. Fine, uniform drops of water, less than 0.5 millimeters or 0.02 inches in diameter, are called drizzle and require about 10 minutes to fall from a cloud 1,000 meters overhead. Drizzle can be so fine that the tiny drops that fall appear to float, and their impact is almost imperceptible. Precipitation, containing the very smallest droplets about to reach the ground, is called mist. Snow is precipitation in the form of ice crystals, or snowflakes, or more often, aggregates of multiple crystals. The size, shape, and concentration of snowflakes depends to a great extent on the temperature at which they form. Recall that at very low temperatures, the moisture content of air is low. The result is the formation of very light, fluffy snow made up of individual six-sided ice crystals. You can see that in the top image. This is the powder that downhill skiers love so much. By contrast, at temperatures warmer than about -5 degrees Celsius or 23 Fahrenheit, the ice crystals join together into larger clumps consisting of tangled aggregates of crystals. Snowfalls composed of these composite snowflakes are generally heavy and have higher moisture content, which makes them ideal for making snowballs. So of course I used an image from the movie Elf. It's a classic. Well, next we have some of the other sort of winter-type precipitations to look at. And just to be clear, there's a lot of words here, but there's an image on the next slide that we'll look at that differentiates each of these. Sleet consists of clear to translucent ice pellets. Depending on intensity and duration, sleet can cover the ground much like a thin blanket of snow. Freezing rain, or glaze, on the other hand, falls as supercooled raindrops that freeze on contact with roads, power lines, and basically any other surface. Both sleet and freezing rain occur in the winter, and they most often form along a warm front, where a mass of relatively warm air is forced over the sub-freezing air. So we can see that in this image again. Warm air is forced above the cold air. Where was I? So, in this case, both begin as snow, which means to form raindrops as it falls through the layer of warm air below. So we need that warm air for it to melt. When the newly formed raindrops encounter a thick, cold layer of air below the frontal boundary, sleet results. In this setting, as raindrops fall through the sub-freezing air, they refreeze and reach the ground as small pellets of ice, roughly the size of raindrops that they formed from. So let's look at that. So we have sleet in the far right here. So snow is it starts as snow, it never warms up enough, so it just keeps falling as snow. Sleet is snow that has melted for some layer, and then it begins to refreeze after a while because it's had enough time to fall from the cold air. These forms of precipitation occur in winter. Let's see, I mentioned this already. If, however, the layer of cold air near the ground is not thick enough to cause the raindrops to refreeze, they instead become supercooled. That is, they remain liquid, or in a liquid state, at temperatures below freezing. Upon striking sub-freezing objects on Earth's surface, these supercooled raindrops instantly turn to ice, creating a coating of freezing rain. Freezing rain makes walking and driving extremely hazardous, and when the ice grows thick, it can break tree limbs and down power lines. So here we see each case. So snow is when it never gets warm enough to melt. Rain is when it gets warm enough and stays warm to stay as rain. And then the only difference between sleet and freezing rain is the time it's spent in warmer air. So everything starts as snow. So we see snow coming down. It melts for a little while, but then it gets cold again, so it can refreeze. Freezing rain melts like everything else does, but in this case, it's got a bigger pocket of warm air to move through. So its temperature is increasing, so it's not going to probably get back to freezing before it hits the surface. Hail is precipitation in the form of hard, rounded pellets or irregular lumps of ice, with diameters of 5 millimeters or 0.20 inches or more. Hail is produced in the middle to upper reaches of tall cumulonimbus clouds, where updrafts can sometimes exceed speeds of 100 miles per hour, and where the air temperature is below freezing. Hailstones begin as small embryonic ice pellets or graupel that coexist with supercooled droplets. The ice pellets grow by collecting supercooled water droplets and sometimes by small pieces of hail as they have been lifted into the updrafts within clouds. Cumulonimbus clouds that produce hail have a complex system of updraft and downdraft. A region of intense updrafts suspends rain and hail aloft. Thus, a rain-free region surrounding an area, downdrafts, and heavy precipitation. The largest hailstones are generated around the core of the most intense zone of the updraft, where they rise slowly enough to accumulate appreciable amounts. The process continues until a hailstone grows too heavy to be supported by the updraft. We just encounter them falling out of a downdraft, as you see in this image, as hail. So the idea is we have moisture lifting up. In this case, we have ice crystals forming. We form hail, and that hail can build up on top of itself and keep building, and eventually it becomes heavy enough that it can't be suspended in air anymore, and it falls out of the storm. Large hailstones often show alternating layers of clear and milky white ice. These layers reflect two different processes by which a hailstone can grow. Termed wet growth and dry growth, as the hailstones ascend, they pass into areas of the cloud where there is a concentration of humidity and supercooled water droplets available. Wet growth occurs when hail collects supercooled droplets quickly, causing the surface of the hailstone to remain wet. As this wet layer gradually freezes, it produces clear, bubble-free ice. Dry growth, on the other hand, occurs when the accumulation of droplets occurs at a much slower rate. The supercooled droplets freeze immediately on contact, trapping tiny air bubbles that result in the milky-looking ice. The record for the largest hailstone ever found in the United States was set on July 23, 2010, in Vivian, South Dakota. The stone was over 20 centimeters or 8 inches in diameter, and it weighed nearly 2 pounds. The destructive effects of large hailstones are well known, especially by farmers whose crops have been devastated in just a few minutes, and to people whose windows, roofs, cars, and so on have been damaged. The United States sees annual hail damage that can run into the hundreds of millions of dollars. And the last type we'll look at is rime. Rime is a deposit of ice crystals formed by the freezing of supercooled fog, or cloud droplets, on objects whose surfaces have temperatures below freezing. When rime forms on trees, it adorns them with its characteristic ice feathers, which can be spectacular to observe. In these situations, objects such as pine needles act as ice nuclei, causing the supercooled droplets to freeze on contact, so when a wind is blowing, the windward surface of objects tends to accumulate over time. Okay, so let's go over a few questions to close this one out as well. Question number 1. What type of clouds consist of sheets or layers that cover most of the sky? Okay, well, if you remember all the way back to our rock lectures, we talked about rock strata. Those are beds or horizontal planes. Well, that's the answer here. That same term is coming about. Strata or stratus clouds are layered. Question 2. What kind of clouds are these? Okay, so in this case, they're puffy, fairly small white clouds. So they're cumulus clouds. They consist of globular cloud masses that are often described as cotton-like in appearance. Fog that forms when moist air blows over a cold surface is called what? Okay, so in this case, it was the advection fog like we saw at the Golden Gate Bridge. And let's see. Last but not least, fog that forms when moist air blows over a cold surface. Oh, I just read this one. What am I doing? I'm sorry. There we go. Cloud droplets remain liquid at temperatures lower than what? So the answer here is negative 40 degrees. Liquid water particles at temperatures below freezing are called supercooled. And, oh, there is one more. I'm losing it. Raindrops can attain a maximum size of blank before they fall. In this case, they need to be at least 5 millimeters in diameter. So that now is the official end of this lecture, lecture 20. And so from here, we will actually start shifting gears to looking at the bigger things in the atmosphere, such as actual storm systems. So, as always, thanks for watching and have a great day.